Next, sum number 5. If R and S are two equivalence relation on a set A, then R intersection S is also an equivalence relation on A. Means I have to prove that if R and S are equivalence relations on a set A, then intersection of R and S is also an equivalence relations on A. Correct? Now the first thing which we need to do here is we need to ensure that R intersection S is also a relation. First we have to prove that R intersection S is also a relation on an A. Then we'll prove that R intersection S is an equivalence relation on A. Correct? R and S are two equivalence relations on a set A. Means R is a subset of A cross A. S is also a subset of A cross A. R is a subset of A cross A. S is a subset of A cross A. Meaning R intersection S will also be a subset of A cross A. R intersection S is a subset of A cross A, and we know any subset of A cross A is a relation on A. This means R intersection S is a relation on A, right? R intersection A is a relation on A. We have been able to prove that R intersection S is a relation on A. Correct? Next, what we need to do is we need to prove that R intersection S is an equivalence relation on A. To prove that R intersection S is an equivalence relation, we need to prove that R is reflexive, symmetric, and transitive. Let's do the first one. Reflexive. To prove R intersection S is reflexive, what we do is, for all A belongs to A, we have to prove that ordered pair AA belongs to R intersection S. Correct? Now, recall, R and S are two equivalence relations. This means for all A belongs to A, I can always write AA belongs to R because R is reflexive. Also, I can write AA belongs to S also because S is also reflexive. Because S is an equivalence relation, so S has to be reflexive also. R and S both are reflexive. So for all A belongs to A, AA belongs to A, AA belongs to S. AA belongs to R, AA belongs to S means the ordered pair AA will belongs to the intersection of R intersection S. Means for all A belongs to A, ordered pair AA belongs to R intersection S, meaning R intersection S is reflexive. Correct? Next, symmetric. To prove that R intersection S is symmetric. So for this, what to do is, for AB belongs to R intersection S, we have to prove, to prove BA also belongs to R intersection S. Right? AB belongs to R intersection S, meaning AB belongs to R and AB belongs to S. AB belongs to R, R is symmetric. AB belongs to S, S is also symmetric because R and S are equivalence relation. So from here again I can write BA belongs to R, and from here I can write BA belongs to S. BA belongs to R, BA belongs to S, meaning BA belongs to R intersection S. So I started with AB belongs to R intersection S, and I have proved that BA belongs to R intersection S. Therefore, R intersection S is symmetric. Done. The third and the last part, that is transitive. Property of transitive. Right? If I can prove this R intersection is transitive also, then R intersection S will become an equivalence relation. Right? What to do? To AB belongs to R intersection S, BC belongs to R intersection S. To prove AC belongs to R intersection S. For AB belongs to R intersection S, BC belongs to R intersection S. If I can prove AC belongs to R intersection S, then my proof will be complete. Correct? Correct? Now, from here, AB belongs to R intersection S mean AB belongs to R and AB belongs to S. BC belongs to R intersection S, meaning BC belongs to S and ordered pair BC. BC belongs to R and BC belongs to S. Correct? BC belongs to R intersection S means BC belongs to R and BC belongs to S. AB belongs to R, BC belongs to R. AB belongs to S, BC belongs to S. But R is, the relation R is equivalence relation, means R is transitive also, and S is also transitive. Now from here, AB belongs to R, BC belongs to R. I can write AC belongs to R because R is transitive, and from the second line I can write AC belongs to S. AC belongs to R, AC belongs to S means the ordered by AC belongs to R intersection S. Ordered by AC belongs to R intersection S. We started AB belongs to R intersection S, BC belongs to R intersection S, and we have proved that ordered by AC belongs to R intersection S. Therefore, R intersection S is transitive. R intersection S is reflexive, symmetric, and transitive. Hence, R intersection S is an equivalence relation. R intersection S is an equivalence relation. Done?